Okay, in this one, we're going to talk about this idea of superposition, the superposition principle for second order linear differential equations. And we're also going to get into the idea of linear independence, which is the fancy way of saying that one function is not a constant multiple of the other function, at least in the case where we're talking about a pair of functions. Okay? So let's go here. So just to recap what we did in the previous video, we had this second order linear differential equation here, y double prime plus k squared y equals 0. And we found, or I shoved down your throat, two possible solutions. Cosine kx, I called that y1, and y2 being sine kx. And I showed you through explicit calculation and really expertly done calculus, if I do say so myself, that in fact this y1 and y2 are solutions to this differential equation here. Okay, cool. Now, and that's what we write here, right? y1 and y2 are solutions. But not only are y1 and y2 solutions, I said that any what's called linear combination of these y1 and y2, which is any expression of this form, a constant times y1 plus a constant times y2. That's what's called a linear combination of y1 and y2. And what we showed is that any linear combination of y1 and y2 is again a solution. Okay? This is true in general for second order linear differential equations. So, and it goes by a certain name, this fact. It's called the superposition principle. So that's what I want to talk about here. The superposition principle. So the basic statement is this. Suppose that y1 and y2 are solutions to the second order linear differential equation y double prime plus p of x y prime plus q of x y equals f of x. No, I'm sorry. These have to be solutions to the homogeneous equation. Yeah, they have to be solutions to the homogeneous equation. Then, any linear combination, also sometimes referred to as any what's called superposition of these two solutions, c1y1 plus c2y2, some constant times y1 plus some constant times y2. I called it a linear combination above. That's more of a mathematician's term. Superposition is more of a physicist's term. They like that one. Either way you want to think of it is fine, but either way you're referring to an expression of this form, a constant times y1 plus a constant times y2, is again a solution. Now I'm going to reiterate the point that I made before. Okay. Okay. Wait. So let me just actually, before I do that, let me make the point. What this is saying is that if you have two solutions, y1 and y2, you kind of get infinitely many solutions by combining them in this manner. C1y1 plus C2y2. Okay? I say infinitely many, but there are some degenerate cases where that might not be the case. So don't hold my feet to the fire if inside your mind you are screaming because of you're thinking of some of these exceptional fringe situations. So just relax, okay? We'll get to them. But this is the essence of it, that from two solutions, y1 and y2, you can build out infinitely many solutions through this process of superposition, if you are a physicist and like physics lingo, or through this building linear combinations if you're a mathematician. Okay, cool. And we could justify this in much the same way that we justified that this superposition of cosine kx and sine kx was again a solution to this differential equation. Should I Dare I? Maybe it is worthwhile. Honestly, maybe it is worthwhile to do this. Okay, I will. Why? Because what is y prime of x in this case? Y prime of x is c1y1 prime plus c2y2 prime. Okay, prime. And what is y double prime of x? Y double prime of x? Well, that's c1y1 double prime plus c2y2 double prime. Okay? And now you just plug all this garbage in to the original equation, and we'll see what happens when we do that. Plug all this data into here, and what we obtain is, so y double prime is c1y1 double prime plus c2y2 double prime, and then we have plus p of x, I'm looking here now, times y prime, which is c1y1 prime plus c2y2 prime, plus q of x times y, which is right here, c1y1 plus c2y2. Okay, yeah, that's what we get for the left hand side. Okay, and what I need to show you is that this is in fact equal to 0. How? Well, let's collect up all the terms involving y1. So we have c1y1 double prime plus, now what do we have? If I distribute this p of x here like this, dot and then dot, then what I get is c1 p of x y1 prime. Do you believe? I wrote it in the other order, so just relax. And then finally, I have this distribution like this, so I have plus c1 q of x y2, y1. Relax. I know what I'm doing vaguely. Okay? Then I've accounted for half of the terms. I have 3 more terms I have to account for. I've got a c2 y2 double prime. I've got a p of x, a c2 p of x y2 prime, and then I've got a c2 q of x y2. When you get old like me, this feels like, sorry, never mind. Let's factor out the c1 from the first 3 terms, can I? I will. c1 times y1 double prime plus p of x y1 prime plus q of x y1. And now let's factor out the c2 from the latter 3 terms. And we get y2 double prime plus p of x y2 prime plus q of x y2. And now what do we know about this and about that by assumption? Because we know that y1 and y2 are solutions to the differential equation. So we know that each of these are equal to 0. And this is where it's crucial that we have a 0 here. And so what this means is that each of these things is equal to 0, and we get 0 in the end. This shows the superposition principle. Yes? Pretty convincing, no? Okay. So the point here now is that, so again, from 2 solutions, y1 and y2, we can build out a whole bunch more through this superposition principle, building out the superpositions of y1 and y2. Now, I want to assert that under a certain in certain cases, you can say something like the following. Because we have C1 and C2, because we have these sort of 2 constants, C1 and C2, that sort of feels like a 2-dimensional set of solutions, right? This harkens back to the previous video where when I was talking about first order linear differential equations, there it felt like we were talking about a 1-dimensional family of solutions. Here I'm talking about a 2-dimensional family of solutions because it sort of feels like I've got 2 constants, 2 knobs that I'm allowed to turn and change the values on to obtain solutions, okay? That feels 2-dimensional. However, we got to be a little careful here. here. Because what if y2 were already just a linear, was already just a constant multiple of y1? Like, what if y2 was equal to 5y1? 5y1 is again going to be a solution to this differential equation, so that's definitely possible. And then what would happen is that c1y1 plus c2y2 would just be some constant times y1. Follow that, please, if that argument, right? If y2 is just 5y1, then c1y1 plus c2y2 is just, well, in fact, what it is c1 plus 5c2 y1. It's a constant multiple of y1 though, okay? So it's not really two knobs it's not really two-dimensional any longer. It's now just one-dimensional. That's very degenerate, okay? That's gross somehow. So we want to be able to have some adjectives to characterize a situation where that doesn't happen. Because we want to know that we really have an honest-to-goodness two-dimensional set of solutions. Okay, so we make the following definition. Two functions, and I'm just starting with two functions here. There's a general definition for any finite set of functions, or even infinite set of functions. Two functions are said to be linearly independent. This is a term that I'm defining here. If one is not a constant multiple of the other. Okay, linearly independent. If one is not a constant multiple of the other. Okay. So, if that is the case, well, let me look at some examples here. Okay, cosine of x and sine of x are linearly independent. Sorry. Okay, why? Why do we know for certain that if I take some constant multiple of cosine of x that I don't magically get sine of x? I mean, it seems ludicrous. If you know the graphs of cosine and sine, you know that if you take the graph of cosine of x, you multiply by a constant, you're just going to stretch it vertically. If it's negative, you might turn it around and then stretch it vertically, yeah? So you will never in particular get sine of x, right? So in particular, if you wanted a sort of argument, notice that so if we take some constant k, or let me say, I don't know, a constant c times, let's take sine of x, right? This is 0 at x equal to 0, right? But cosine of 0 is 1. So if c times sine of x were equal to cosine of x, then when we plug in 0, this side is equal to 0, but this side is equal to 1. So I guess, and we know sine of right, that's a contradiction right there. Sorry, I don't know what happened to my brain just now. Yeah, that's a contradiction right there. In other words, that can't be the case. And so the assumption that c times sine of x is equal to cosine of x is absurd. Okay? That's the idea. So in fact, cosine of x and sine of x are linearly independent. All right? Let me give you another example. If you take 0 and any other function, these are not linearly independent. Why? Because I can always exhibit a multiple of f of x, which is equal to the 0 function. Because 0, in fact, 0 is equal to 0 times f of x. And that shows it. What I've done is shown you this here. This is a constant multiple, the constant being 0, of f of x. And it's equal to 0. So no matter what the other function is, if 0 is included in your set, then you're not linearly independent. Okay? All right. Cool. So in particular, and here's the point about linearly independence, okay? If y1 and y2 are linearly independent solutions to a second order linear differential equation, then c1 y1 plus c2 y2, that is to say the superpositions, are a two-dimensional family of solutions. We know that any linear combination is a solution from the superposition principle, but now they really kind of like point in different directions, right? One is not a constant multiple of the other. Think in terms of vectors, maybe, if you know something about vectors. If one is a constant multiple of the other, then span. Do you know the word span? We'll learn. Maybe you don't know the word span. But if one is a constant multiple of the other, so there's something one-dimensional about that, yeah? Whereas if the two vectors kind of point in two different directions, then there's something kind of two-dimensional being sort of constructed there. Okay, yeah? Okay, well, great. So this really is a two-dimensional set of solutions in the situation where y1 and y2 are linearly independent, okay? Last point that I want to make before I end this particular video. Gosh, what was that last point I wanted to make? Oh, yes, it's this. In fact, in most situations that we are going to encounter, in particular, if in our second order linear differential equation, so remember we had P, Q, and how do I want to say this? Maybe let me say it in a different way. Sorry. I just thought it through, and I need to say it in a slightly different way. You know what? I'm going to put this in the next video. Sorry, I wasted your time there for 30 seconds. My bad. Yeah, let me make this point in the next video where we'll talk about existence and uniqueness of solutions and say a little bit more about linear independence. Okay, see you in the next one.